Okay, in this video we are going to make a binary tree with Python 3. Now keep in mind this is just one way of creating a binary tree. A binary tree, the concept is conceptual. So you can have many different types of implementations of binary trees. So the one we're going to make this time is class-based, but there are lots of different ways to make binary trees and lots of different ways to maintain them. So this is just a very, very simple kind of introduction to binary trees. The idea of a binary tree is that it's a data structure where you have a root node that stores some type of value. So the nodes are the circles, and the value is inside of those circles. And each node also has an attribute that holds a pointer to another node. So this is the left pointer and then the right pointer. So the left or right attributes. Now the left attribute points to another node, and each node has a left and right attribute. The leaf nodes are on the bottom, and they do not have any left or right attributes. So these two would be called children of this node. This would be the parent of these two nodes, right? It's a hierarchy. So these two nodes are children of the A node, and the A node also happens to be the root node. Now if you look at this, A is a tree. It has a root node and two children, and it splits off. Each of its children are also, in and of themselves, a tree. B, if you consider it to be the root node, it has left and right children. Right? Even D by itself is a tree, even though it has no children. Okay, so every tree has two subtrees, left and right. Okay, so again, this is kind of a loose abstraction. The idea of a tree can be written into code many, many, many different ways. Okay, so we're going to just look at one of those. All right, so first we're going to kind of make a loose framework in Python 3. I have this file. I've got the hashbang, so it'll run if I run the file directly. And if the file is run by itself instead of imported as another file, that's what this line does, then we'll execute this code here. So generally you might use this type of code to test whatever library you're building. So we're building a tree, so down here we're going to write our tests, right? So to start with, we need to make a node class. All right, so the node is a simple class, and we discussed that this is the constructor or initializer, and that always contains the self parameter, and then you want to pass in a value as well. Value. All right, so self dot value should equal whatever we pass in. So this is an attribute we are adding to our node object, our instance. Okay, so self represents one particular instance of this object. Alright, so we're adding a value property and setting that value property equal to whatever we passed in as an argument that gets stored into the parameter value. Then we have two other attributes, self.left, and that's going to start out as none, and then self.right, and that is also going to start out as none. So what this would essentially be, if we create one of these nodes, down here we're going to test. If we create one of these nodes, this is just going to be essentially an empty tree. So if I have node equals node, right? We now have one node by itself, and that is essentially enough for a tree. There aren't any children, so going back to our picture here, that would just be the node A. We need to pass it a value, so we could pass it the letter A, and now we have a node with a value of A, but it does not have any children left or right. Okay, so the entirety of the tree would just be this node. And we could continue to add nodes, right? So we could say n2 equals node v, and then n.left is going to point to n2. I might call this B, A and B. A, B. So A dot left is going to be pointing to B, and then A dot right, we could say, is node C. So at this point we would have a tree Go back to our image. We have A, and A dot left is equal to the B node that has no children, and A dot right is equal to the C node that has no children. So we're manually constructing this tree just by using this very, very simple node class. There's not much else here. All right. But what we're going to do is we're going to make another class that represents the tree and makes use of this node class. And that's because this other class is going to have helpful functions that we can use. Functions that will allow us to traverse the tree. It'll have properties that'll keep track of the length of our tree, how many nodes are in our tree, and lots of different other things that are going to be helpful when we're using this tree class. Okay, so this node class is very, very simple, and you can essentially construct a tree with just nodes, but you have to do it all manually. See how we're wiring this up manually? A dot left equals B, A dot right equals the node C. That's a very manual process. What we can do is make this tree class and make everything a little bit more automatic. Okay, that's what we like in computer science. So class, and we're going to make tree. And what kinds of properties do we want this tree class to have? Well, it's going to need to have a root node to point to, right? So let's make our initializer, our self property, and it needs to have self.root, and that is going to be the beginning of our tree, and it'll start out as none. All right, and then we also need a length property, self.length, and it's going to start out as 0. All right. One of the common special attributes you can override in Python is the __len__ property. This allows you to use the length function, the global length function that's built into Python 3, and you can return whatever you want. So in a binary tree, what does it mean to say the length of the tree? Well, that could mean a whole lot of things. It could be the height of the tree, it could be any number of things. But for this particular binary tree that we're making, we're going to call the length of the tree is just going to be the number of nodes, and we're just going to return this property, self.length. Right? Return self.length. Okay, so very simple so far. We've got a couple of properties here. All right, so now what we can do is we have this tree class, very simple, and we can make a tree class. We'll say t equals tree. So this is one instance of a tree class. We have instantiated a tree object. Okay, we took the tree class and called it with left and right parentheses, and that makes one instance of the tree object, and it gets stored in the variable t. So now T is sort of a wrapper around all of our nodes. The nodes themselves are what the tree class actually is, right? When we talk conceptually about a binary tree, the nodes are the important part, right? But this tree class we're making is sort of a wrapper around that functionality that gives us extra properties and extra methods that we can work with. Okay, it kind of wraps up all the nodes together and keeps them in one nice place. All right, so what we can do here is we can say t.root equals node A, and then t.root.left equals node B. Oh, and after each one of these we have to say t.length plus equals 1. All right. And then duplicate that line, dot right equals node C. And then add 1 to our length. So here we have the root node of our tree, t.root. Root is an attribute of our tree class, this instance. We're setting that equal to a node, a new node we created. And then since we now have a node in our tree, we have to add 1 to the length of our tree. Right? And so what we can do is we can print out a few things to see how this is working. First of all, we can print out the length, and we can say len of our tree, and that should be the same as saying t.length. Okay, but this function here, __len, when we override this function, that allows us to use this length, or when we define this function, it allows us to use this len property like we would for an array or a string. Right? So we'll print that out, and we can also print out t.root.value, t.root.left.value, and then t.root.right.value. And we could even go one more, t.root.left.left.value. Well, actually, there won't be a left.left, so we'll just leave off that dot value. So t.root.value. So this is going to be the root node, and then the value of that root node, which will be a. Then this is going to be the root node's left property, which we set that to node b, and then the dot value is going to be the actual string b. So this would be the node, and then dot value would be the string. So here this is t.root.right, which we set to the node c, and then dot value is going to be the string c. And then t.root.left.left shouldn't exist, and if it doesn't exist, by default we set dot left to none. So this last one should be none. And we'll just test this out real quick. Python 3, or we can just run it directly. Bin tree. So length, and we see both of those ways we can get the length of our tree, and here we have printed out our tree, A, B, C, and then none. Okay, so let's go ahead and add a few more items to our tree here, and so we can do, let's see, copy this. We want dot left to equal node D. We want dot left dot right to equal E, and then dot right dot left to equal F, and then dot right equal G. Okay, so what we have done here is we've essentially made this tree, right? So we can double check that. We can look at how we made this. T.root, so our tree's root property is going to be a node, and that is going to be node A. Node A, T.root's left property is going to be a node, and that node is going to be B, right? T.root right, that right property is going to be a node, and that's C. Then we have root.left.left, so root.left, this is going to be a node D. Root.left.right is going to be node E, so that's left.right. And then root.right.left, so root.right.left is going to be F, and then root.right.right is G. So we're manually constructing a binary tree here just using the node classes, but this is tedious, right? Especially considering we might have a node of 100, or a tree of 100 nodes. Could be 1,000 nodes, could be 1,000,000 or 1,000,000,000. Really big data structures are used these days for searching and all sorts of stuff, and binary trees are common. This is infeasible to use this manual construction for very large sets of data. So we're just doing this right now to make sure that our classes are working the way we want them to right now. But ideally we're going to have some sort of method here on the tree class to insert items, right? We want to insert things, and then that way we don't have to do this manual wiring also. So that insert is going to have to make use of some sort of loop, because it has to find out where this item is supposed to be added. Now again, this gets into binary trees. There are lots and lots of different types of binary trees. We were making a very, very simple example, and the way we add items in our binary tree is we keep our binary tree complete and full. So that means basically we fill one level at a time from left to right. So the first node we add is the first level, A. Now that level is filled. So we go to the second level when we add an item, and we start on the left, and then go right. So A, and then we go to the next level, B to the left, and C to the right. Then we go to the next level, D, E, F, and G. So this is sort of a breadth first. They call this breadth first, where you explore the breadth of an individual level before you go to the next level. The breadth of one level is all the way filled before you go to the next one. So there are different ways of adding items to a binary tree, and this is just one of them, so keep that in mind. And the way you add items to a binary tree can give the binary tree different properties, and that is some of the power we have in binary trees as well. So this is just one method of constructing a binary tree, and there are lots of ways, including one of the most common ways is just to construct a binary tree as if it was an array of data, and then you can just calculate index values and keep the data structure of the binary tree conceptual. So in our case, we actually have a node and a dot value and a dot left and a dot right. In other cases, you could just have an array, and you could have a dot left method that would calculate the appropriate index of that array to find the left child, and then a dot right method that would find the appropriate index of the array to return the right value from the array. Right as in R-I-G-H-T. Right, so lots of different ways to make this. So again, this is just kind of introductory way. A common way of adding items might be this breadth first traversal kind of way. All right, so we've got this manual construction here. One of the things we're going to need to do is print out what the tree looks like. Okay, that's going to help us to make sure our methods, when we add items, make sure that they're in the right spot. So we're going to want some sort of method that's like a tree dot, tree print or something. And there's lots of different ways you can do this. I can make a function find tree print, and I have to add the self parameter. And what we can do here is basically we start with self.root. We have a current node, and that's going to be self.root. Okay, and while current does not equal none, right? We could loop through and print out the items a couple of different ways. If we wanted a breadth first way to do this, we would have an array visit. Okay, and we can put the root node in here, self.root. We could just do a while loop. While there are items in this array, so while our visit array has items in it, so while length of 0 is greater than, or length of visit is greater than 0, we could also just say this, because if this is in a while statement, 0 and it's 0, it would get converted to the Boolean version of 0, which is false. But we'll go ahead and be more expressive and say if the length of the visit is greater than 0, then what we want to do is we want to pop off one of these items. Right, so we'll take off an item, and we'll say, let's see, node is going to equal visit pop 0. Right, so that removes an item from our list, and then we want to add the items to visit if node.left. So if it has a property, so if that does not equal none, then we're going to add that to our list. And node.left. Right. And then if node.right does not equal none, then we add it, append it to our visit list. Okay. But at any rate, once we have one of these nodes, we might want to print out the value of that node. So print node.value here. right? And then this should add items one at a time, left and right. So if we look at our tree here, we start out where current is self.root. We actually don't need that line now based on the way we're doing it. So our visiting array starts out with just root node in it. We pop that node off and we say, okay, print out that value. Now if there is a left value, we're going to add that to the end of the list, and there is, so we add the node B. And then if there is a right value of our node, we're going to add that to the end of the list. So we do, right? And then the while loop says, okay, do I have any items in my list? Yes, we added 2 new items. So we're going to pop off B, and we're going to print that out, and we're going to add a left and a right item. Okay, and then we're going to loop again, and we pop off an item. Do we have any items left and right? Yeah. So we've gone A, B, and C, and now our visit node has these 4 nodes in order. Okay, and then we go to D, pop that off, print it out, and we go to the left. Is there anything to add? No. To the right, is there anything to add? No. Then we go to the next node, we go through the loop again, right? E, F, and G. All right, so this should just print out. This is what we call a traversal, and this is actually a breadth first traversal. But this is just one way to show that our tree is being printed out accurately. We're printing out what we think. We're constructing the tree properly, because the next method we're going to add is the insert method, and we want to be able to make sure we can visualize the tree, and we'll have to double check and see if the insert method is working. Okay, so we'll do this. Get my spacing right there. All right, that looks good. And we've got tree print down here. So let's call this in tree, and A, B, C, D, E, F, G. Okay, so that looks like it's actually printing out a breadth first traversal, which means everything's hooked up properly. Okay, so that's one way you could print out the tree. All right, so there's another way that I have that's a little bit more advanced, and it prints out a tree a little bit nicer. It's kind of outside the scope of this, but I'm going to use that instead. So I've got a different tree print function I'm going to paste over here. Okay, so I'm going to take this and paste, and it makes use of a tree print recursion function. And again, this is sort of outside the scope of this demonstration, but what it does is it allows us to look at the tree a little bit better. Okay, so this, you can just, for now, just think of this as some sort of black magic or voodoo. You can look at it if you want and try to figure out what's going on. It's not too terribly complicated, but it might be, for a beginner, it might be a bit much. Okay, so all this is going to do is print out the tree, and we'll see it does a much better job than just printing out the elements like this. So it requires the math library, though, so we need to go to the top and import math. There we go. All right, so I'll hold it on here, and you can pause, and if you want to, you can copy all this down. It is a really nice way of looking at your binary trees in the terminal. Okay, so take a minute and pause and copy that down. All right, so now we'll just print out the tree again, and we'll see that it looks a little bit different. Let's see, get value. I have to add a couple things to get this to work. Okay, so one of the things we need is we need to get node. So I want to get one of a particular node from my tree, and I want to do this by index. Okay, so the concept here is if we had, we're not keeping track of any indices, but if we think of the index of this item as index 0, 1, 2, 3, 4, 5, 6. So we want to get a node based on some index value, and that's how we're numbering. We're numbering in a breadth first manner, so our indices are numbering the values in the tree in a breadth first manner. So this get node method is going to do that, and then we have a define get value method, and get value is the same concept, it's index, but instead of getting the node itself, we just get the value. So what we can do is we can say return self.getNode, index, and then whatever that returns, we can call dot value on. Okay, so once you have get node, get value is very, very simple. All right, so how do we make get node? There's a couple things we need to do really quick. So first, we're going to check to see if the index they provided is out of bounds. So we're going to have to check our length of the length of our binary tree. All right, so we're not going to make use of negative indexing because we could. It's just a little bit more advanced. So we're going to just keep it with positive indexing. So if the index they provided, right, this is the index parameter, this is what they provided to this method. If that index is less than 0, or if the index is greater than or equal to the length of the tree, so length of self. So don't forget that self is just one instance of these of a tree, right? And because we're inside of the tree class, so whenever we use self, that's an instance of this tree. So it's different depending on which instance. I could have 100 different instances of the tree, and self would be different. There would be 100 different selves. All right. So if index is less than 0, or the index is greater than the length of the tree, right, then that's basically means the index is out of bounds. We don't have a valid node in that range, right? So what we can do is raise an error, and we can raise an index error specifically, and we can say index out of range. All right. So let's go down and we'll comment out print tree because that's not quite ready yet. But we can say t dot get node and or even get value, and we want to get a value at -1. That should give us an error. Index out of range, so that's good. If we get something, so how many items do we have? 1, 2, 3, 4, 5, 6, 7. So there's 7 items, so if I try to get the item at index 7, that should be too big. 6 should be the largest index value. So we should also get an error here. Out of range, that's good. And going up, we don't have anything else, so I can add a number, but it's not going to really do anything. But we're going to add a number that is in range, so we should not get an error this time. None type has line 30. Oh, that's because I did get value instead of get node. It doesn't have a dot value property. So get node 5. Right, so that worked. We don't have an error. So that just means that our exception handling here is working. Right? Is it out of range? Is the index out of range? If it is, we raised an error. All right. So now what I want to do is I want to get a node, and I need to locate it. I'm gonna get a node in a breadth first manner, kind of like we did on that first print tree. All right. So I can say I is an index 0, and I have a visit queue, and I'm going to put root inside of that. Now we all know a queue is just like a line. The first one in the line is the first one out of the line, right? So when you're at the bank or something like that, you get in line. Whoever is the first one in line is the first one who gets helped. All right, and then we have the current node, and we can just say that starts out as visit queue dot pop. Right, so this is basically adding an item to the list and popping something off. So while I is less than the index that they provided, we're going to perform these steps. Before, we were printing out the entire tree, but here we're trying to just find one particular node, right? So we don't need to keep going once we found it. Okay, so this could kind of be considered a binary or a breadth first search. That's kind of what we're doing here. But instead of searching by the value, we're searching by an abstract concept index, right? If we kind of made up this idea of an index. We're not keeping track of these indices anywhere, but we're saying the root of the node is index 0, then that's index 1, 2, 3, right? So we kind of made this syntax up here, and now we're implementing it. But the idea is similar to a breadth first search. All right, so inside of this while loop, if current node dot left, right? If that does not equal none, then we're going to add to our visit queue, append the current node dot left, and then same thing for right. So I'll copy and paste this. If current node dot right does not equal none, then we'll append current node dot right. And then don't forget to increment I. So what we're doing here is I is just something we're using to keep track. We start at index 0. They give us an index, and that might be here. This index might be this value. This is, I think, index 5, right? So we start at I equals 0, and then we search in a breadth first manner, and we keep increasing that value of I until I equals that value they gave us, and that's how we know we're on the right node. Right? So I starts out at the root node and goes in a breadth first manner until we reach the index they provided us, and then we can return that node. All right, so at that point, if I is no longer less than the index, that means I is equal to the index, which means the current node is the node at that index, because we need to keep updating current node. Right? So current node has to change each time in the loop. So that's going to be visit node, oops, the visit queue dot pop 0. We're going to pop off that first item. Right? So you add the root node to the list, and then pop off an item. If the current node has a left, you add it. If it has a right, you add it, and then you pop off an item from the list again. Right? So I is always the index of the current node. And the current node is the node that we're searching. So it'll be A, then B, then C, until we find the appropriate one. So whenever this stops, whenever this becomes false, that means I is going to match the index that they provided us. And it's also going to be associated with current node. So whatever index they provided us, our variable current node is now going to be holding the node in that variable, the appropriate node, right? So what we want to do here is just return that current node. Okay. Now there's no reason this shouldn't work if everything is coded correctly. We checked to see if the index was in range, and as long as the index is in range, our particular binary tree is not allowed to have gaps in it. Right? We have a complete binary tree, which means we fill it out from left to right, one level at a time. Now this would give us errors if we had a different style of binary tree, in which we did allow gaps in the tree. All right, but for what we're doing, this should work. So get node, we can test that, see if it works. Let's go down here. Get node 5. We'll make this get value now, and we'll print it out. Get value 5, and that is the item F. All right, so if we look at our binary tree, 0, 1, 2, 3, 4, 5. The item at index 5 is F. Okay, so that gives us the get node and get value. So that, the get value, that allows us to now use this tree print function. All right, so again, this is kind of the voodoo. You can take a look at that, and we'll uncomment print tree again, and we'll see how this looks. We don't need these either. So we've just got print tree. Okay, and so now you see it kind of prints out a nice binary tree, sort of like this image. You have A at the top, and then it's 2 children, B, and then 2 children there, C, 2 children there. Okay, so this, that's what that print tree and print tree recursion method does. Alright, so now we know we can construct a binary tree and we can actually print it out to verify that it is actually connected the way that we think it is. Alright, so now what we need to do is add an insert method. Alright, so let's add an insert method and then we can get rid of all of this. And then we'll take a break and do more on the next video. Okay, so we have get node, we need to insert get node and get value. Those are kind of related, so we'll keep them together, and then we'll say define insert. And we're going to use insert, it's going to be similar, it's a similar API to the array or the list in Python 3, right? So the way insert works in Python 3 is actually, we're just going to add an item to the end. So this should actually be append, but we'll call it insert. So this is just going to insert an item at the end. So we're not going to deal with an index value. So we'll have value, and we'll pass for now. Okay, so insert is basically going to allow us to, we're going to insert A, for example, and it's going to do all of this for us. It's going to automatically connect the node in the right spot. So if we had a tree like this and I inserted H, the structure should automatically find where it goes, and it should go to the left of the D node and add it in there. Okay, so that's kind of the idea. That's where we're going to go to next. Let's see. So once we get finished here, we won't need all of this code. We can just insert a whole bunch of items, and it'll be something, we'll have some sort of for loop down at the bottom where we can just go through and add items. So for example, I could say the ASCII ordinal, the starting place is 97. If you look at the ASCII table for lowercase a, 97 is the ASCII ordinal, and then I could have a certain number of items that I want, so a number of nodes that I want in my binary tree. I could say that's 15, and then I could say for I in range, and the range is going to start at 97, and then it's going to go to 97 plus however many nodes I have, number of nodes. So basically this is going to be a list of 97, 98, 99 all the way through until we have 15 ordinals, and then we're going to convert those ordinals to the character representation, which will give us the actual letters that we're looking for, A, B, C, right? So what we would do there is we call our tree.insert method, and what are we inserting? The character representation of that number I. So I is going to be 97, the 98, the 99, right, all the way through a list of 15 of those. Character function turns that number into the ASCII character represented by that number, right? So we're just inserting items into our tree, character representation of that ASCII number. So with this, I'm basically going to be doing this, but not manually. So our insert function has to handle all of that. And I could, what's nice about this is I could, you know, go up to 26. I could go much bigger, except the you know, the ASCII thing is going to break. I mean, I could do something like, you know, I could do a mod to see if it's greater than, you know, 97 plus 26, and if it is, set it back to 97, and then we'd loop through, and the children, if the tree got really big, the 27th child would be A again, 28th child would be B. You know, you could do something like that. But for our purposes, for this demo, we only need 26 is plenty of characters. We don't need any more than that. But we could also just put in numbers too. That might be an easier way of doing this as well. So anyway, this will work once we have t.insert. Okay, so we don't have that yet. So we need to define how we're going to insert items into our tree. Okay, so first thing we want to do is we're going to get a new node and create that node with whatever value they supplied. Right? Now there's a couple of cases that we need to consider. Right? The base case, if the length of self, it's not a base case, but it's the if the case in which the tree is empty. If the length of self equals 0, so a tree has no 0, there's something special we have to do in that case. That special thing is, say, self.root. We have to set the root, and you only do that when you insert an item and there's nothing in the tree, right? So you only do this one time, and it's when the tree is empty. So self.root is going to equal this new node, and then we can't forget to add 1 to our length. So self.length plus equals 1. All right, and in this case we have completed inserting a node, so we can just return. All right, so this is the special case. Empty tree insertion. Okay, so that's the only time we have to do this special case, and it's because of this self.root property, right? You only modify that when there's no other nodes in the tree, right? So any other case, once we get here, we know we have at least one node. All right. So in this case, we need to look, and we're going to kind of do what we did before, kind of this type of strategy. All right. So we'll start with, we're going to go breadth first and find some items. We'll say I equals 0, and visit queue, and that's going to have self.root in it, and we know we have a self.root. If we don't have a self.root, then we're in this section, right? And then we add a node and return. Okay, so we know for sure that this is an item and this is a node at this point. All right, and then the current node is going to equal visit queue dot pop 0. Now obviously this is sort of kind of a wasted mechanism. You added the item to the list and then removed it, right? But the reason I do that is because within the while loop we have to do that. So I'm trying to mimic the behavior that we do in the actual while loop, right? We have the current node equals visit queue dot pop. And we can do pop 0 then, and then here pop 0. All right, so we're going to have a while loop just like we had before. While I is less than self.length or the length of self, either one. If current node.left append so if we have this value, if it does not equal none, then we're going to say visit queue dot append, and we're going to add current node dot left. And then we'll do the same with right, like we did before. Current node dot right. Okay, but there's something a little different we need to add here. And we'll go ahead and finish up too, and we'll say current node equals visit queue dot pop 0. So popping the first item from the list, and then I plus equals 1. All right, so this is kind of the normal way. This is pretty much exactly what we have here. So the difference lies in this. If current.left does not equal none. Well, if it does equal none, because of the way we're going through one node at a time in a breadth first fashion, as soon as we encounter a node where its left property or its right property is none, then that means that's where we need to add our node. Right? So as soon as we get to D and we say D.left, that node dot left, if that's none, that's where our new item must go. Right? So if this equals a node, then we just add that node to our visit queue. Otherwise, else current node dot left. So this case, else, current node does not equal none, we do this, but this is the case where it does equal none. So current node dot left, there's nothing set there. So we are going to set that new node, right? And then we add one to our length, self dot length plus equals 1. Right? And then we can just return, and that will break us out of the loop as well. Okay? So we don't have to keep going because we found where our new node goes, and we don't have to continue iterating through. We don't have to, at this point, if we were at D, in our visit queue, we would still have these 3 items. But we found where we're supposed to add our new item, so we can just stop. And so we just return. Right? But it's the same for visiting the right. Right? So if we have a current node.right, and that is a node, this is essentially saying if current node.right is a node, then we add it to our visit queue. If it's not a node, meaning if it's null, right? Or if it's none, so otherwise, else, right? Otherwise, current node, and it's basically this code right here, current node except .right is going to equal the new node. And then self dot length plus equals 1 and return. Okay, so this is the insert function, and it's basically just the breadth first strategy, right? So this is common to do a breadth first strategy. You have a visit queue, and you have a while loop, and you keep adding items to that queue until you locate the item that you want, or you've gone through the entire queue. All right, and if we wanted to, we could put a return down here, but we don't have to because we're not returning any values. Return. That just tells us that's the end of the method. Okay, this code will actually never get reached because we'll always hit one of these. This is more of a visual thing, so you can see when the end of the function is. All right, so now we test this out, see if it's working. We're gonna comment out all of our manual tree construction, and then we will uncomment this. All right, so as we said, we went over what this is doing. This is adding the characters A, B, C, and you can have whatever you specify as number of nodes. That's how many items we'll add. So 15, if I run this, we see we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And we can go as high as 26. And then we run out of characters. Okay, and you can make it lower, 6. But this is a nice visualization. It lets you see how the tree is constructed. A, B, C, D, E, F. Okay? So that is the insert method. And so now we don't need any of this. We don't need any of that manual construction anymore. All right, so we've got print, we have insert, and we have get value and get node, and we have a length function. Okay, so this is a pretty good start. And the next time we're going to continue on with some additional methods, some traversals, some binary search, and that sort of thing. All right, so that should do it.